Welcome, everyone. And I would like, first of all, to thank for the opportunity to be presenting here this really interesting topic that we've been working on for the past couple of months. So, my name is Henrique. I'm an electrical engineer by education. I did my bachelor and master in that area, but started focusing more on humanoid robotics later in my university career. And I specialize in the areas of integration with other systems, virtualization, and interaction. And I started at Accenture directly after college. At the beginning, I was kind of like, oh, consulting. But Accenture does it in a bit more different way. So we really go into the applied part of technologies. And as you will see today, we really do tech. And it's a really interesting area that we work in because we do tech innovation and we incubate new technologies that we can then apply and deliver to our client. Elias?
All right, yeah, that's me, Elias. I'm also part of the Next Gen Robotics Department. So what we focus on is to bring this new generation of robots into spaces where robots have not been before. So, for example, to public spaces, hospitals, airports, and so on. And I mean, it's interesting also for you guys as students. How did I get here? So I studied industrial engineering, and then during my master's, I did a lot of students projects in the robotics lab. And so when I started my work at Accenture, I already knew how to program robots and how to write code. And I think that's also quite important. And so on the presentation today, why next-gen robotics? First, why is there a new generation of robots? There has been some technology shifts in the last few years that are making new robots possible that haven't been possible before. And one of these technologies that is coming up is virtualization, that we see making a huge difference on how we program robots. And so we will firstly explain why virtualization and simulation, and then we will dive into the practical part. So how do we use, or how have we been using Nvidia Omniverse in the last year to make a difference when we work with robots, and then also looking into the future and lessons learned. So why virtualization? This is actually a really interesting topic. So here a market quote. So by virtualizing problems, we will be able to solve real-world problems at the speed of the digital. So what this means is we can simulate real-world environments in a simulation. And since we have to simulate it, we can gather a lot of data from the simulation. And then this allows us a new engineering approach because we can iterate over design decisions and have a KPI-driven approach. And so the key why virtualization is because we don't have the constraints of the physical world, and this is allowing us a lot of interesting engineering applications. And so how is this applied? And what is this enabling? So firstly, it's custom AI development. This is one that's really in the beginning, because we have all this data available in the simulation, we can train our custom AI agents. We have an example on this later, and we can accelerate the development of robotic applications in general. And also, since we're able to simulate our problems, we can also mitigate deployment risk before, because we can simulate the environment that we're interested in, and then we find out before we do the real-world deployments or the issues that the deployment could have. And another one is the area of digital twins, where you basically have the clone of the real environment in your virtual environments, and then you can do real-time collaboration and so on. There's a lot of space opening up. And so if virtualization is so important and interesting for engineering, why is it not much more important already? And there are two reasons. Firstly, technical reasons. For example, when you want to virtualize real environments, this is still costly and expensive. So you need to do the 3D design and so on. And then there's also non-technical challenges on the market. And so one is, for example, the market fragmentation. So for each simulation, there are a ton of different simulation providers. And often they're not compatible with each other. And also, from the robotics perspective, many robot manufacturers have two businesses. Firstly, the hardware business, and then the software business. And so it's kind of siloed. You cannot use the the software from one manufacturer with the hardware from another manufacturer. And also often they have their different languages and their different approaches. And so it's really hard when you're an expert in one simulation tool to switch over to another one because the framework is so different. And so with this, there's a new kind of player on the market that is approaching this differently, which we explored, and that is Omniverse.
Yeah, exactly. So Omniverse has been around now for, I think, 3 years, but it first became a viable option to work with, I think, January last year. And that's when we really started looking into it. But what exactly is Nvidia Omniverse? So Nvidia Omniverse is a platform created by Nvidia that is, in its base, a collaboration application that allows you to do 3D development, simulation, and it bases around the universal scene description, so USD files, which is a file format with which you can store 3D models and other types of information. But it's not only this, because this allows you for a really tight collaboration and to integrate a lot of different platforms. So Omniverse is built up of 5 key components. First of all, we have the nucleus. You can think of it as the core of NVIDIA Omniverse because it allows this type of collaboration. The nucleus is a database that it's either hosted locally or in the cloud, where you store your USD files. And why is this so important? Because by having it at central location, if I'm, for example, creating a 3D model of a chair, and Elias is creating a 3D model of a room, and I make changes to my chair, and his room has my chair, this will automatically update my model in his room. And he can then also go back to different versions of my chair and choose a version that he likes the most. So this type of collaboration is really important and really helps speed up the development. And this is not only for 3D designs. This is the same for robotic simulation or for whatever you're developing in Omniverse. Then the second part is Connect. Connect allows you to integrate other platforms. So for example, you might know Blender, a really well-known open source platform for 3D design. You can live sync your designs from Blender into NVIDIA Omniverse. So if you do a change in Blender, with a little bit of latency, the model will be changed in NVIDIA Omniverse, which is a really interesting capability. Then you have Kit, which is basically a Python SDK that allows you to create your own applications in NVIDIA Omniverse and customize your experience. So you can change the layout, you can create applications, plugins, whatever you want. Then the RTX renderer, which most of you might know RTX from ray tracing technologies in gaming, but in this case, we're applying it to real world simulation. And last of it, we have the simulation part. Because it has a really accurate physics engine, you can simulate most things of the real world in simulation: fluids, people, robots. And what are the fundamental capabilities of Omniverse? So photorealistic rendering, you can render really accurate environments. You can collaborate. So as I said, I can work with Elias miles away and we're collaborating on the same platform. We can simulate features. Let's say I'm building a robot and I want to test out a new wheel size and I want to see how the controllers of that specific robot are going to behave. I can build AI and ML components, and Elias is going to go a bit more in depth later on this, but I can generate synthetic data there or train the whole models, for example, with NVIDIA Tau. I can extend the platform with the kit, so I can create applications there. And lastly, I can connect third-party ecosystems. And NVIDIA builds on top of all of this. So we have the ecosystem applications, 3DMX, visual components, Unreal. We have the NVIDIA core part, so the application itself with Viewer, Composer, and Isaac Sim, which I will talk a bit later. And then you have all the platforms which are used to view all this. And what is Isaac Sim? So Isaac Sim, for us robotics people, is the core part of NVIDIA Omniverse. It's a robot simulation engine that allows us to use a wide variety of different things like Replicator to generate synthetic data, Jim to do reinforcement learning in robotics. For those who know it, it's a really big topic. Cortex, which is its own library for robot collaboration. So you have multiple robots collaborating to each other in the simulation. Mission Dispatch and Client. Most of you might not know what VDA 5050 is, but VDA 5050 is a standard right now for AMR communication, which is a really fragmented market. And in NVIDIA Isaac Sim, you can simulate this communication. Co-opt is used to optimize routes, and most of you might not know what vehicle routing problem is, a really well-known problem in the optimization community, and NVIDIA has its own approach to solving it. And lastly, ROS and ROS2 integration. ROS, for those who don't know, is a robotic operating system. And it's basically the language and programming style that allows us to program robots. And most robots in research are programmed in this way. And also some in industrial applications even have this as their core capability, core backend. And now, enough of the more boring stuff. We're going to show you a couple of examples of things where we have been applying NVIDIA Omniverse. And the first one was the project that we worked on this summer. It was approximately 6 weeks. So you can see that how much we built in 6 weeks because Omniverse already has a lot of these core functionalities. So this project, we called it the AMR Optimization MVP. This might look like a really general buzzword name, but what we did here is with NVIDIA i6 we created a plugin. So it's basically an attachment or a small plugin that you put into i6 that allows you to speed up the process of simulating AMRs, autonomous mobile robots, in order to speed up the commissioning. So let's say you're a big company that wants to create a warehouse, but you don't know exactly how many robots you need or how you should design the warehouse for these robots. So you need to simulate it. And in NVIDIA i6 with such a plugin, you can do the simulation. And what we wanted to do here is to prove that it's possible. So what we did is we created this plugin that eases this process. So I'm going to show you a bit how it works. The video is a bit long, but I'm going to talk a bit through it and talk to you about what we did. So basically, when you're simulating AMRs, you need to tell them where the AMR can go. So here you can see NVIDIA i6 with the custom plugins we built on the right. And it's as easy as loading an application. So you just open the extension and load whatever you want to use. And here we have two applications. One to create the scenarios. So basically tell, okay, this is the model that we want to use. So we take, for example, a 3D model of an environment. In this case, we took a warehouse. And then we have to say, okay, where can this robot go? Because the robot, we could do and say like, it's an open space, go wherever you want, but you want to optimize it. So for this, we need a waypoint list. A waypoint list basically enables us to tell the robot, okay, you need to go through these points in order to achieve something. And you need to pick objects from A and take it to B. Because in warehouse, that's everything that you want to do. You want to pick up objects and put them in another part of the warehouse. And traditionally, to create this waypoint list, it's a really boring thing to do. It's a JSON file with a lot of XY coordinates. And what we did is with Kit from NVIDIA Omniverse, we just sped up this process and created an app where you can just drag and drop points and lines and connect everything. And this might not look like it saves a lot of time, but instead of taking maybe 1-2 days per room or per environment you want to do, we took like 5 minutes. And it really speeds up the whole process. Let me just, sorry. I need to go to the screen. Exactly. So you can then basically create your waypoint list really, really easily. You can copy everything, and within 5 minutes, you're going to get not only your waypoint list, but also the list of tasks you want to do. So now I'm going to skip to the core component of what we've been working on. Give me a second. And here you will see, like, again, we've just loaded our warehouse, and we want now to load the scenario that we're testing. So I just loaded the waypoint list, a small one, only 200 points. And then I load the orders. So you can see like red is a pickup, green is a delivery. And then we also load the robots. In this configuration, I said, okay, we have 3 robots. Each of them can carry 200 kilos and has a battery life of approximately, here we did it in meters. So I think it was 14.5 kilometers. And then we created our own optimizer that took all of this information and told us what is the way and the fastest and best way to solve this. In this case, it told us, yeah, you only need 1 robot. You don't need 3 robots. So you can already get an idea of why you need to do this during commissioning, because each robot costs, let's say, 50K. You don't want to buy 3 robots and then discover on site that you don't need them. You need to be able to plan this kind of thing. But only knowing the roots is not enough, because you need to test the robotic software stack. And this is what we have here. Here we're launching ROS. So you can think of ROS as like the robot backend, the brain, where we have navigation stacks, vision. Everything is running. And why are we then testing? Because then I can simulate this robot and simulate the robot going around the factory and see where maybe things are kind of messed up. Like, where does a robot get stuck? If it goes through the factory or warehouse or everything, and nothing happens, then you're happy. And you can see maybe this robot, okay, it took 1 hour to perform all this. What happens if I take a robot that is faster but has less battery life? Could I take 2 robots and do it in half the time? Or will it just not be good enough? And I should take the robot that carries more and is slower. So what I did after is I stopped the simulation. I was kind of like, okay, let's try it with a robot that has less battery life and see what happens. And I think, yeah. And what you're going to see is that it's pretty easy. I just changed the text file. I said this is an MVP. We wanted to prove that it's possible. It's not yet commercial or anything. But it's as easy as changing a text file. And I think most of you, if you're electrical engineers, you've used VS Code. Pretty simple. And I just upload the new version. So new map, new robot, everything. And I can just press optimize. And you will see that we now have a different rule. We have 2 robots. The blue one and the orange one, I think. Yeah. And then I can just simulate the 2 robots. And I can see like, okay, these robots have the same navigation stack. When you have more robots, you have more problems because they can collide against each other. They can collide. Their navigation stack might not be good enough that they can interact with dynamic obstacles because they don't know how the other robots will behave. And you can see what will happen. We took a basic navigation stack. So the robots, they can work autonomously, but if, for example, a corridor is too narrow, they don't know how to go around it. So we know that we need to change the navigation stack. Or we need to tell the robots that 2 robots can be at the same time in a corridor. So you can see what's happening. It's kind of chaotic. But this is why you need simulation. This is why you need to do this before deploying. I think questions are at the end. And in the end, you can generate a lot of data. So you can see here like heat maps. You can get information on like how much time the robots took to perform certain actions and everything. So, yeah. And why is this all important? So basically with all of this, you can get a lot of information on the robots and can improve the optimization, and can optimize your deployments of robots. And this is not only important for warehousing, but we also did it for a hospital. So you can easily change the scenario and apply it wherever you want. Yeah. Sorry. I'm going to give it over to Elias.
Yeah, interesting. So one example is here, we designed this warehouse in the beginning, and we thought this is perfect for robot deployment. And then when we actually ran simulation, we realized that we needed to change the layout because the robots always got stuck. And this is exactly why it's so awesome when you simulate before, because if you need to change the real layout, it's super important. It's super expensive. And the way, since we simulated this, we were able to evaluate this beforehand. And this is one key part of the value proposition of doing using the simulations in practice. And another example of the value of this simulation tools is synthetic data generation. And so the new market for next-gen robotics is, one large component is computer vision. And the issue is when we, for example, have an inspection case where the robot needs to walk around and needs to detect, for example, fire extinguishers. When you need to train this computer vision model from scratch on real data, that's super expensive, and also the project timeline for doing this is quite long. And so this summer we created this pipeline to train computer vision models on synthetic data. So we use also Omniverse here to put 3D assets in, and then we generate synthetic images from the simulation and have trained the CV, the YOLO model on the synthetic data. So how does it work in detail? Real quick, you have this 3D model. We have here an example of a Coke can that we use, and then we add other objects. In this case, actually, we also did it with Blender, but we found that Omniverse has a bit higher performance when you do the synthetic data generation, and then you place the other objects in the simulation, for example, on front of the Coke can, and then it's partially covered. And this allows you to get much higher accuracy in detecting the object. And so synthetic data generation is a huge field in itself. but it's super interesting. And so the output here is we have 1,500 images that are already labeled, because in the simulation you have this already. This is just something you can set in the settings. And usually labeling images is also super expensive. It takes a lot of time. And here you have the labeled set of images in about an hour. And then we do the model training, some image augmentation, and so on. And at the end, we have this model, and we also, for the CoCan, this is why we have the example, we also generated a real data set to benchmark the performance. And we found that we were about the same accuracy when we used the synthetic data than when we trained the model on the real data set that we had. And the business case here is clear, right? We have the CV model in below an hour. It's deployable on the robot, and it's comparable to having real data. And the good thing is with Omniverse, this is mainly created. It's a super high accuracy. It's really like real life. So the images look quite realistic. And so it's really transferable to a real world example. And they also have a lot of scripts and so on that you can use. And so we found this to be really valuable for one of the business cases that we have. I'm just showing this to you live here. Starting. So firstly, we made this really simple to use. So we have this GUI here. I'm starting it up. And then we load in the 3D file. There's a lot that can go wrong with 3D files. So we build in a viewer that you can see that it's actually working. And then we start the training. You can see here, this is how these images look like, these synthetic images. And then we have a script afterwards adding the labels. And then this is our robotics lab in Munich, and I have a few CoCans sitting around just to demonstrate how this platform works. And then we could deploy this on real robots. And on synthetic data, there's a lot of more interesting things that we can talk about, but we don't have that much time. And with this, also jumping a bit to the future, because there are some interesting applications coming up. So large language models don't only have an understanding of the world, but they also have a locational understanding. And this is not a native Nvidia capability, but that's something that's coming up. So what you do here is you have this interface, and in this initial scene, let me jump back. We had this chair below the table, right? And now we give this prompt, move the chair to the right of the table, and then it computes a bit. And then you will see the chair being generated to the right of the table. And then we say, add a cabinet at the right of the room. And after some time, it will add the cabinet there. So in the future, maybe we could also auto-generate these 3D assets. Right now, we can't. So right now, it just uses existing assets. But this is also an interesting application. And this will maybe also simplify the way we interact with these simulators. So this is one very interesting development in the space. I can wait for it to show at the end. For the sake of time, let's jump to the next one. This is also interesting. So since we do robots in public spaces, one important field for us is human-robot interaction. Because industrial robots, usually they have these cages, so they don't have to deal with robots. And this new generation of robots needs to be able to interact with robots. And Nvidia Omniverse offers this avatar cloud engine. And that's really pulling together all the latest research in this space. So you can have your own chatbot, your own NLP. You have the video. And I actually showed this to you live before I go further. Jumping here. I hope there is no advertisement. Yeah. So what you can see here, this is actually not Isaac Sim from Nvidia. This is Unreal, MetaHuman Unreal from the Unreal Engine, because they have this approach of partnering with other companies. And since we don't have a sound right now, we don't see how realistic the lip movement is, for example. But even like the movement control, there's so much that you can do with this cloud engine. And that is super important for us, or super interesting to simulate the human-robot interaction, and something that might be coming up in the future. Let me jump back. Go to the latest stage. Exactly.
Yeah. Maybe before you go on, I just have 1 or 2 points about what Elias just presented. This collaboration with Unreal is enabled because there is a connect. So there's a live connector between Omniverse and Unreal. So this kind of work is what Nvidia Omniverse really focuses on, is collaborating among different tools. And the other point I wanted to mention is the synthetic data generation project that Elias mentioned. If you already have a 3D model of your environment and you want to add a new model, and you want to test this computer vision or AI module on your new robot, if you already have an existing simulation because you've built your robot in simulation, then it's really easy to test the new AI models. And NVIDIA Omniverse, because they already have all of these base capabilities created, really eases your work, because if you already start with it in the beginning, then the development gets really easy. And that's why accelerated development cycles is one of the biggest reasons to use such simulations from the beginning. Sorry, didn't mean to interrupt a lot.
Yeah, that's awesome. And this were just some examples on how we use NVIDIA in the last year to help us bring this new generation of robots to reality, to public spaces. And so what did we learn in this journey? So we addressed the challenges before. There were two kind of challenges, right? The technical challenges. And those ones, I think, NVIDIA Omniverse is really cool because NVIDIA is doing a lot of research in the space, and that usually becomes pretty soon available in NVIDIA Omniverse. For example, this lip sync that I was talking about, that's a very recent paper, and you're already able to use this now in Omniverse. And so as soon as something new gets developed, it's really quickly available in Omniverse, which is really cool on the technical side. And on the non-technical challenges, they had a few ideas on how to address those. So on the market fragmentation, we have different simulation providers. They're not compatible with each other. And NVIDIA has this approach of partnering with everyone. For example, for the simulation one, they also have a people simulator. But in this case, they use Unreal because they kind of pull together the strength of the different simulators. For example, there are discrete simulators, and they have then, you can start with the discrete event simulator and then import your stuff in Omniverse, for example. But this is also in the beginning, so they're just building this up, and often there are some limitations for this, since this is a recent development. And then on the hardware silos, they don't have their own hardware, right? And so they are vendor agnostic, but they have a ROS integration, and you have to do a lot of work yourself. So, for example, in the video that Henrique showed, he spent like 2 weeks building this robot from scratch and doing all the connections. And so it's very open, but it's not plug and play in many cases. That might change when NVIDIA Omniverse is really a dominant platform, but right now this is still a hurdle that we have.
One quick thing to mention is that it isn't plug and play. There's a lot of work involved there, and the documentation, because it's an ever-changing software, is not always the best. But with all the sources you have online, you eventually get there. And the important thing is it took us 6 weeks to create that plugin, that simulation, with all of the parts we've done. I've worked with a couple of simulation engines, and the classic ones like Unity, which is also used to Gazebo, which if you're from robotics, you know Gazebo. It's not an easy task because you don't have the basis to do this. And with Omniverse, because even though it's still pretty recent and a lot of things don't work as well as you would expect, it really eases the work with it. And the ROS integration, of course, if you've ever worked with ROS, it's not easy. There's 1,000 different versions for everything, so it takes time, but it helps speed up the process.
Exactly. Yeah. And then on the last part, on the training part, so this is somewhat addressed-ish. So Omniverse also borrows many approaches from different simulators. So it's okay to get used to, but you also need to train up a bit before you're really able to fully use the platform. And also on the documentation, there is a lot of work you have to do yourself still and figure out why the paths are broken and so on. So don't plan to have it running. If it's something advanced, you have to have some development time. So, but also it's a very early platform where all the new technologies are being pushed in. And I think that's also part of the game when you have the latest research in such a platform.
Yeah. So thank you everyone for your attention. I think we're now open for questions if there are any. Oh, cool. And yeah, if you have any doubt, interest in this area, feel free to contact us on, I think that's LinkedIn. And yeah, it was a pleasure talking to you all today, and thank you.
So we have some questions. Is Nvidia Omniverse going to replace the use of the game engines like Unity in robotics?
You can take it to your more with Unity than I.
Okay, so it's not. As we said, Connect is a big part of Omniverse. So you still want to do, like, if you use Unity to develop a part of your game engine, or let's talk simulation, not talking gaming in this case, you're still going to use Unity. Unity is your preferred platform. So if you're used to it, there is a connector in Omniverse, still better, to import everything from Unity. Same for Unreal. And as Elias said, Omniverse is not one platform that works as a single entity. It's a collection of different platforms. So of course, Nvidia is developing Omniverse, but it relies a lot on other technologies. And it's the same with Unreal and with Unity in this case. There are some parts that might be replaced, like Unity has a really interesting ROS integration for those who work with ROS, but Nvidia Omniverse also has its own. So if you can use the ROS integration from Unity and then just live stream everything into Omniverse and use the photorealism from Omniverse. So if you want to get like really photorealistic images or videos of your robots moving around, but you prefer Unity, you can use Unity. We've been testing out Omniverse because we want to get to know the state of the art, and it has the support for a lot of things nowadays. It's not going to delete what has been done in the past. It's going to extend it and complement it.
If someone wants to start with the robotic simulations, what are the first steps where to start?
Someone wants to start? Yeah, I think the first step is just to get started, actually. It doesn't really... I mean, there are different simulators, and each simulator also has a different purpose. And so for robotics, for example, Gazebo, Omniverse, we use these physics-based simulators. And getting started with one of them, I think, is a good first step because they are also really similar. Also, when you need to do the ROS integration, it always works a bit the same. And then there are also, for example, the discrete event simulators, which I think are a bit more harder to get started with because often they're not free. So for a student, that's better to do this. Sometimes they have some student license, but I think for university projects, going with this physics, so for example, Gazebo, Unity, or Omniverse, I think would be really interesting to start.
Yeah, but if you're doing like really robotic simulation, even before that, I would really suggest the ROS tutorials. If you're not yet into ROS, they're comprehensive. That's how I started a couple years ago. I think you probably at some point did a turtle tutorial. For those who know, the turtle tutorial is like the most well-known robotics tutorial. And then you can move on to Gazebo and Omniverse. And it's really, it's an interesting journey. And there's a lot of documentation because, as I said, robotics development is not easy. So there's a lot of people online complaining and helping you out.
Is simulation accurate to real robot behavior? Aren't there unknown parts that are hard to simulate, like fallen box in the warehouse, etc.?
Oh, that is a very interesting question. Yeah. So the sim to real gap. Is not necessarily negative. So you can abstract a lot of the complexity of the real world, and then you can actually solve problems quicker in the simulation. And so it has a good side, but it also has a negative side that quite often it's not directly comparable. So it's possible, but it's a lot of work to have like a one-to-one comparison. And even then there might be a tiny gap, because when you work with real hardware, with robots, for example, then sometimes the motors don't work fully. And in simulation, usually you have more an idealized. You're able to like also approximate, but it's always when you move to the real world, then you always have some issues usually. But it's not all negative, I would say.
And also depends a bit what you want to simulate. So if you're going like really low level on a robot and you're like simulating the gears and the drivers, there is a sim to real gap. If you're simulating like more high level things and you just want to test your, I don't know, navigation stack, or you want to test your task assembly stack, those are things you can do pretty easily in simulation. And of a box falling, I think that's okay in Omniverse, because even I've seen it done too. It depends what you want to do with it. If you want to test your AI module on and identify if the box is falling, then you're testing your AI module, and that's basically a video. But you can also test it in real world. You always test in real world, but you start in simulation.
And the last question, how do you simulate weight? How do you assign them to the objects? Do you need to do it manually? How do you simulate interaction, speed, and weight force for robots in the environment? Code for iOS or Omniverse import JSON assigned by hand?
Yeah, that's a lot of Okay, so adding weight to objects in simulation is, if you have created the object like a USD file in Omniverse, you just import it. So you need to assign weight, and that's simulated in the physics engine. So that's the core component in Nvidia Omniverse. Second part of the question. So when you import a ROS-enabled robot, there is a URDF importer. URDF is a standard file design for robots in ROS, so you can import it. You can also create it yourself, and then you have to assign mass, you have to assign inertia, damping, and everything. So that's why it took me 2 weeks to create a robot. It was the first time of me like really doing it from scratch. And yeah, there's still a lot of things that you have to do by hand. But that's why, for example, we created a plugin, because there's plugins for everything in Omniverse. So eventually someone will create a plugin to speed this up. I think I got most of the question.
And I think also this is one of the things that always can go wrong. Maybe the weight is not accurate. So sometimes we created the robot and it didn't drive. And one of the reasons was, for example, that the weight was, well, the traction or something like this was off. And so working with simulation can also be complicated, but working with robots is always a bit complicated. There's always a lot that can go wrong, but also when it works, then it's really awesome.
Yeah, funny story. Elias went on vacation for a week, and during that week, my robot would only turn right for a full week. And it took me like building the robot twice to understand that the weight distribution of one of the models that I had taken from a library just had twice the weight on the right wheel. And this took a week because it's not easy. And you can't find anything right away, but you can identify a lot of problems if you simulate. So if I would have built this robot just out of the tech sheet in the real world, I would have noticed in the real world that something was wrong and would have spent a lot of money by building it. But I did it in simulation, so it only cost 1 week and a bit of my mental sanity of watching a robot going around for a full week. So this is a really interesting lesson learned from my side. Always simulate a bit beforehand.